So the operations that I tackled in the previous video were a little on the simpler side because they were for Math 92. I'm going to do a couple of harder examples more at the Math 96 level. So same principles apply in terms of our operations, right? Multiplication, if we're multiplying two radicals together, as long as they have the same index, we can just put all of whatever our product was. Let's say this is star times circle. We can put that inside of the radical symbol. Same thing with division, because division is just multiplying by a reciprocal. We can go ahead and rewrite this as one quotient under that same radical. Only thing is our radicals have to have the same index. And then for addition and subtraction, we need like terms. So we need to simplify first to see if we have like terms. So the first question I have here is a pretty challenging one. There's a number of ways to tackle it. I want to talk about a more efficient way versus a less efficient way to do this. So the less efficient way to tackle this problem would be to start trying to simplify each of these first. It's less efficient because while there are pieces that we may be able to pull out, like we can see, we could pull an x cubed out of this and a y squared, and same thing over here. Now we have more things to multiply, and then when we finish, we may end up with something that we can multiply, something in our radicand still that needs to be simplified again. So essentially we'll end up simplifying 3 times. So my recommendation when we're dealing with a product is not to simplify each of the different radicands, but instead to create one giant monster radical. So we'll make one giant cube root with all of this inside. One thing to note, we don't need to multiply out the numbers, especially if we're going to use the prime factorization or the factor tree as a method. So I'm going to go ahead and leave the 24 and the 18 separate. There's no reason to bust out a calculator and figure out what giant number that is. It's just going to make life harder on myself. But I am going to combine up the variables. So x to the 10th times x to the 7th, we're going to add those exponents. We'll get 17 x's. Same thing with the y's. We'll have 12 y's. And now we can go ahead and do our simplifying. So for the variables, that should be simple enough. We can use that trick of how many times does 3 go into 17 so that I don't have to write out my big list of x's like we did in the simplifying section. So we'll have 5 x's come out front with 2 x's left behind, right? That's just the remainder. I'll tackle the y's next. 3 goes into 12 4 times. There are no leftovers, so we'll just have a y to the 4th on the outside. And then the last thing we have to tackle is what happens with the numbers, right? So this is why I like to keep these two separate. And if I was smarter about this, I wouldn't have written my answers right below. But I'm just going to leave them separate. Essentially, I've already done the first step of my factor tree. That's why I didn't multiply them. And now I can keep going. 6 and 4. I'm going to just, one thing to know right away is that when we take the cube root of a negative, we're going to end up with a negative on the outside. So I'm just going to go ahead and move that negative sign out here to begin with and ignore that as I make my factor tree. 18 is 6 and 3, 3 and 2, 3 and 2, 2 and 2. And we are looking for perfect cubes here. So however you want to do it, if you want to rewrite it as the prime factorization or you just want to look for those groups, looks like here we've got 3, 3, and 3. We got one group of 3's coming out, so I'll put a 3 on the outside. Oops, that's not my black pen. In terms of our 2's, there's a set of 2's there, so I can bring a 2 to the outside. And right, this is all multiplied. And then I do have one sad friend here, this 2, that didn't have a buddy to leave with. So we do get a 2 stuck inside of my radical. Don't forget the index on your radical. And then, of course, we can simplify this all up. Ooh, I'm outside of my range now. To something pretty. The 3 times the 2 should be a negative 6. Making sure it's obvious that the 3 is the index on the radical, not a power on that y as well. And we get 2x squared stuck inside. So just a way to kind of deal with some of these gnarlier problems a little more efficiently. Like I said, don't multiply numbers out, leave them separate. Don't simplify early because then you're just going to make yourself more work. So let's tackle another problem. So I actually gave you 2 different problems here so we could see the 2 versions of the quotient rule moving in both directions. Feel free, pause the video, try these on your own. But first things first, we should recognize on this first one that this 2 is just a coefficient out in front. It needs to stay in the denominator. If we wanted to, we could almost rewrite this thing as 1/2 times this square root of 75x all over the square root of 3. Now, whenever you're presented with a quotient of two radicals, a radical divided by another radical, as long as they have the same index, so in this case they're both square roots, it probably makes sense to not leave them as two separate radicals. Our life would probably be better if we wrote them as just one radical. So just boop, and then simplified that fraction. Now, if you recognize that you can do that, and you can simplify within this already, you can do that. But students will sometimes, if this had been like a 5, will want to simplify the 5 into the radical above. So just be careful. One of the ways to keep yourself from making that mistake is making sure that you rewrite so that now you can simplify. And so this will now be 1/2 times 25x, the square root of 25x. And hopefully we recognize that 25 is a perfect square. I don't need to make a factor tree to see 5 times 5. So I can bring a 5 out to the outside, and I'll get 5/2 square root of x. And this is the same thing as writing 5 root x over 2. These are identical. It just sort of depends which format you like better. There isn't necessarily, I think, here an agreement on which is better looking in terms of simplified. Personally, I like this version because then I'm looking at a coefficient next to a variable factor versus this where I have two different operations happening. But that's just my personal preference. So I kind of like the first one, but it's completely up to you. All right, so the second quotient here is written as a single radical, which means it's probably more efficient to break it up into 2. So if I see something written that has a fraction inside of a radical, my first instinct is, well, let me just try rewriting it this way to see if it makes my life better, right? Oops, I almost forgot my 4. And then I can deal with each of these little pieces. The variables here both are multiples of 4, so I can see my variables are both going to be able to be simplified and come on outside of that 4th root. The 48, on the other hand, is a little bit gross. For the 4th power, I kind of look at this. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. I know my power of 2 is probably the one that's going to work in here. So 48 is not one that I would want to make a factor tree, especially with a 4th power. Instead, I would look at my 4th powers and basically say, oh, does 16 go into 48? And I can recognize 48 is, ooh, is this still within my viewing window? Is a real question. Yes, 16 times 3. So that way I can see, oh, so this 4th root of 48 is the 4th root of 16 times the 4th root of 3, and this is just 2. So I just wanted to show that like sometimes the perfect powers are easier to work with than making an entire factor tree. Since 48 is such a small number and the 4th root is such a giant power that I'd be looking for, I would use my perfect powers over my factor tree. So anyways, bring out a 2, because we just said the 2 comes out, bring out the A, and that sad 3 gets stuck left in there. And on the bottom, we end up with C squared. And now you can see why it's so important that this 4 is like on top of the little like piece of the radical, because otherwise it would look like a to the 4th. And again, this is a completely correct answer, but you could also rewrite it like I did in the last question, where you had the sort of square root of the 4th root of 3 off and had a fraction. But in this case, this is probably a little bit cleaner. All right, our last example for these sort of more intense operations with radicals is one where we're going to use our addition and subtraction as well as multiplication. All right, so I chose this one because I liked the idea of having I don't know, some extra stuff kind of going on here. We've got our addition and subtraction, and we're going to have multiplication at the same time, and we have coefficients out in the front, right? The simplified versions. So we're going to treat this like any other binomial times a binomial. We're going to FOIL it, which is a 4-letter word in math. So I'm going to distribute each of the terms. So first term, if you need to, you can always write this out. I'm going to have that square root of 2 times the square root of 5, and I'll move slow. The second one, plus square root of 2 times 2 square root of 8. And then we'll distribute the second term, not forgetting that it had a negative attached to it. So negative 3 root 8 times the square root of 5, and negative 3 root 8 times 2 root 8. So, like I said, you could do this in your head, but I'm moving slow just in case anyone needs a little bit more help. So now we're doing that product rule from the very first question. So we're just going to go ahead, as I said, for the most part, it makes sense to go ahead and do the actual multiplication, or at least rewrite this. I can see here 2 and 5 are both prime. They have nothing in common, so I'm just going to go ahead and multiply those to 10. No reason to leave 2 times 5 inside of there because I can't break it down any further. I'm not going to get any perfect pairs. The second one, though, remember here, we're going to multiply any of the constant parts, so there's 2 of these, and then we can bring in, basically what we're doing is we're using, I can never remember what the different rules are called, the associative rule or property, saying I can multiply, this is a bunch of stuff all multiplied together, and I can multiply them in whatever order I want. So I'm going to multiply the 2 first, and then I'm going to multiply the 2 radicals together so that they can combine. So that's the reason we're just going to go ahead and say the 2 stays out front. So if you want, you could rewrite this as 16. You could have left it as 2 times 8 and done a factor tree, but I can already see the square root of 16, well, that's just 4. So I'm going to have a 2 times 4 for this second term. Moving on down, we're going to get a 3. It's the square root of 40. I'm thinking 40 looks kind of evil. Maybe if I had simplified that 8 ahead of time, I'd be in better shape. But again, when I'm doing multiplication, I might have ended up with extra work. I would have had to do 2 different simplifications in the previous term. So I'd rather just do 1 simplification at the end. And then our last one here, we've got to multiply the 3 and the 2, so we got minus 6 square root of 64. And if you recognize the square root of 8 times the square root of 8 is just 8, you can move there immediately. But we know this one here is a perfect square, so we'll have 6 times 8 for this term. The only one that we need to clean up is this 40, because I recognize that we have a 4 and a 10 there. And so this square root of 4 should come out as a 2. So your final answer for this one should look like this. Square root of 10 plus 8 minus 6, because this 2 came out and multiplied with that 3. Square root of 10 minus, oh, that hurts, 48. Simple math is not my forte. And they go, oh, wait, that's really not my final answer because I have a lot of like terms now that I simplified everything. The root 10s, I have 1 root 10 minus 6 root 10s. So there's negative 5 root 10s. And for the number portion, I have a positive 8 and negative 48. So I end up with a negative 40. Typically, when we write these, we usually write the piece without the radical first. This is just to keep our lives simpler in terms of sometimes it's hard to tell when students or when people end their radical symbol. So if we write a number term out in front or any other terms out in front, it's more obvious that they're not part of that radical. Either of these is completely fine though. They are the same. So anyways, those are the more advanced operations that are more in line with the 96 level of what you're expected to know moving into a Math 104 or 116.